coming today. If everyone can hear me okay, I won't use the microphone. I've been told I'm quiet. So, okay, so today's presentation, I guess there's a lot of interest now in the industry on trying to improve the efficiency of processing operations. There's large reductions in grade historically, so we're treating material that's much lower grade. And what we're looking at are opportunities to use the latest technologies to improve the quality of material going to a process plant. And one of the applications is a real-time sensing and then making decisions based on those sensing results. So this presentation focuses on the sensing technology, how it works, what it does, and then how it's being applied to various operations, particularly at New Afton copper gold operation. I'll talk a bit about the history of why they thought the sensing would work and some investigation work that they did, and then how it's been implemented and where they're at the moment. So typically we find that we need to explain the technology in most audiences because they're not all aware of the technology's capabilities. So we typically do a bit of that. Then we talk about some of the other applications, of which this is just one of many. So we need people to be aware of that. We haven't designed this equipment for bulk sensing, for bulk diversion or bulk ore sorting. That is just one of the applications of this technology. And then we can talk a bit about New Afton and then just summarise. So why do we need this technology, or why is it applicable? And the reason is because ore bodies have variability. If ore bodies were all homogeneous, we wouldn't need to worry about process engineers. We wouldn't need to worry about real-time control, feedback, reactions to changes. We would just have a nice manufacturing plant. And that is one of the main differences between manufacturing and the mining industry. Manufacturing deals with controlled inputs. The mining industry deals with a highly variable ore body. And it's not just variable in the way it's mined, but its quality, the flow rates to the mill. So there's a whole lot of parameters that vary, and what we're trying to do is just look at some of those parameters to try and measure them. For us, it's the composition. So if it wasn't for the variability, we wouldn't need to develop these technologies. Having said that, there's very few measures of variability we can currently use that will help decide whether this technology will be useful. And that is one of the big problems. It's very easy to look at a block model and say, okay, we have a block with a certain grade or quality parameters. We have another block, but because it's an averaging process, you find there's not much variability between blocks, and these blocks could be thousands of tonnes or tens of thousands of tonnes. What we're measuring at is a much smaller scale. So we're saying, well, but what's the variability every 10 tonnes? And the block model won't give you that. So you have to go back to drill hole assay data and say, what's the variability down a drill hole? Because that is the level of detail we're seeing on a conveyor and measuring in real time. So that's sort of the context of why we need to do a bit more investigation to understand variability in an ore body scale. And it's not just the variability in the ground, it's what we do with that material. We mine it, we dilute it, we leave bits of ore behind, we stockpile it, pick it up and we process it, hoping that it's homogenised, which it never is. So what we're looking at is some sort of a pre-concentration application here where we can remove undesirable components of the flow between the mine and the mill so that we don't have to treat those. And if we can remove waste to upgrade the material, produce the same or more concentrate from less tonnes of feed, that's a good thing. The key thing with variability is we don't want to homogenise the flow. We want to retain the variability so that when we measure it, we can then respond to it and remove or make decisions based on those measurements of short increments of flow. So we can remove waste, we can remove deleterious material, we can stockpile low grade, high grade separately, and then we can control what we feed to the process plant. So the way we want to do this, ideally, is in real time. Now, part of the sensing technology also really requires that it's representative. There's no point having a sensor that's giving you ballpark figures, but not really in a meaningful, representative way that you can make decisions, that you can be confident in making those decisions based on some sort of data that's generating. So what we need is a method that's accurate, representative, reliable. We can have high confidence in the technology. The advantage of the sensing technologies is they're very good at measuring conveyed flows because it's an ideal presentation to the technology. It's very hard to measure a haul truck because the configuration of that haul truck isn't ideal for most sensing technologies. It's okay if it's uranium grade and you can put a scintillometer there and detect the signal given off by the truck. That's great. But we can't do that for copper ore or lead zinc ore or gold ore, so we have to come up with other ways of measuring that material. The advantage on a conveyor is the continuous flow. We can measure using a technology that's transmissive, so it penetrates the full flow across the full cross-section of the belt as it's moving along, and we're measuring continuously through the material, and we're generating multi-elemental results as short as every 30 seconds. So the short measurement increments means that we can make decisions on small tonnages. So that increases our selectivity in terms of bulk diversion or bulk sorting, which is what this presentation is all about. So what we're looking at here is, when we talk about sorting, most people have in their minds particle by particle. What we're looking at here is basically looking at increments of material. So it's not really sorting, it's diversion of an increment, but it's a bit like an automated grade control. So the focus here is on bulk measurement, decisions on bulk increments, not particle by particle. And effectively what we're doing is trying to decide or divide that flow into different components that we want to control. So some of that material could be better ore that we want to process earlier in the mining timeline for that operation. We might want to put poorer ore to a different process or a different stockpile that we're going to treat later. We might have different ore. We might have sulphide and non-sulphide material that can go to flotation or leaching. So there could be different processes that apply. There could be highly deleterious material we just don't want to process. Copper grade might be great, but the talc content could be 20%, so we may not want to process that material. And obviously waste. If we can get rid of waste before we process it, fantastic. Less material going to the tailings, less reagents spent, less power, less grinding media, everything. Any waste that we don't process has huge benefits to the operation. So what we're effectively doing is an automated grade control on a conveyed flow. Instead of a geologist looking at a haul truck and saying, yeah, that truck loads ore or that truck loads waste, saying, well, we don't necessarily need to do that anymore. We can put everything on a conveyor, we can measure it accurately, and we can make decisions on every maybe 10 tonnes. And that's an objective way of measuring based on an elemental content. I'm not saying I'm a geologist, I don't want to make geologists redundant. I think there's still a lot of requirements for geologists, but I'm saying that in a grade control application like this, maybe there can be less geological input. Some of the material might be suitable for upgrading via other processes. For example, if you have a high-grade ore that's diluted, it might be very amenable to particle sorting or dense medium separation or some other method of upgrading that material and then putting it back into the plant so that the waste component of that is thrown away. There's a whole range of benefits which you all are aware of in not processing material unnecessarily, so I won't go through those. So let's talk about the technology. So the technology is not new. Okay? It's been around for 30 years. on a conveyed application. It's been used in the coal and cement industries for over 25 years. It's been used for laboratory analysis back into the 60s, as far as we can find, probably earlier. The key aspect of the technology was prompt gamma neutron activation analysis. Okay, so prompt gammas is what's produced from the neutron activation process, and we're analysing the spectral data from a series of detectors which are above the belt and from a source that's underneath the belt. Now we use californium-252. It's the most prolific generator of neutrons that's available. It's currently the most expensive substance known to man, but don't let that bother you. We only need a small amount, so we use 50 micrograms to start with. It has a short half-life of 2.65 years, so every 2.5 years we add another 25 micrograms to the unit to get the activity level back up, and then it decays over 2.5 years, you top it up, etc. So the level never goes below 25 micrograms, which is the basis for our performance estimates for each element in terms of measurement accuracy. So we sort of get better than that most of the time, but that's the minimum, the worst accuracy we go down to. So californium generates about 115 million neutrons a second, so it's an ideal source of neutrons. In fact, we even slow them down to help the process, because the way the technology works, it relies on two parameters. One is how well each element can capture a neutron, and that relates to the neutron's energy. So you can also produce neutrons from a neutron generator. It's just that they're 10 times higher energy, so the neutron capture, that process we need to happen to measure an element, isn't as efficient. So a californium source is the ideal source of neutrons for this technology. The element gets excited when it captures a neutron and gives off gamma radiation. Measuring that gamma radiation by its energy level helps us characterise the element via the peaks represented in the spectral signature that we're collecting. As with any technology, you can supplement or complement with other technologies. So with the elemental system, we use another technology, which is a microwave moisture measurement. It's great measuring elements, but you probably want to measure them in dry weight percent. So measuring the moisture as well as the elemental gives us the correction back to dry tonnes and gives us the ability to send the information to the plant in dry weight percent for each element, total element, or as it's common oxide, depending on which element we're reporting. In minerals now, we have had installations since 2002 in the iron ore industry, so we have close to 85 installations now in about 10 different commodities. I haven't included the coal and cement sector in those because this configuration is a much higher specification than the one we use in coal and cement. And that's part of the problem if you're looking for a unit these days, is that there's a lot of vendors. So each vendor will say, well, we use PG and AA, and by definition, because there's 80 installations that are successful, it will work in your mine. The problem is, different configurations will not work. So it has to be configured appropriately to the mineral sector, and it has to be custom calibrated to each application. You can't use a off-the-shelf calibration and achieve the sort of performances I'm going to be talking about here. So that's what the system looks like. It's effectively a C-frame that slides around the belt with shielding attached to that, tunnel shields either side. The whole system is 3 metres long. The moisture analyzer at the front here is just a simple microwave system. Doesn't need shielding. It's a 0.1 watt microwave field, so it's not hazardous. Doesn't heat the material up. It doesn't do anything to the material on the belt except get affected by its moisture content, and that's what we use to measure moisture. So the elemental system is usually mounted on a conveyor with a walkway. You can stand next to that unit. The level of radiation on the outside of those tunnel shields is the same as 10 bananas. Okay, so, however, in Queensland, we've got to put a fence around it and we have to use a small source. But you can walk into any supermarket, there's no warning signs around the banana display. It just shows that regulation in the mining industry is out of control. This is just what I explained. Radiation source is the green dot, very big green dot for a 50 microgram source. It's equivalent to the size of the end of a pencil, or that silver bit on that plug. It's about 12 millimetres long, 6 millimetres in diameter, double encapsulated piece of Californian wire. Costs about $70,000. These numbers are from a copper mine, Sepon, so the grade is real. Their average copper feed grade is about 4.2% copper. These results are every 2 minutes. As I say, the source is the green dot, the neutrons are the yellow dots coming out. The material absorbs those neutrons, the gamma emissions are given off, and the detectors at the top. Could use the detectors, so they detect the emissions given off. The advantage of the design is that these idlers support the unit, support the flow and conveyor through the area, through that tunnel, so there's no contact in here with the unit, there's no wear components, there's no contact with the material of the belt, so it's extremely low maintenance. And this design is one that's evolved over many years. Other units might have similar designs. We have a patent on certain aspects of this design, and it's been challenged, but we've been successful in defending that patent. So why PGNAA? Okay, we know PGNAA is fully transmissive. We know it's elemental. We know there are other technologies, XRF libs, near-infrared, laser-induced fluorescence, X-ray transmission, magnetic resonance. There's a whole range of technologies out there that don't give you the same capability as PGNAA. Magnetic resonance and X-ray transmission are penetrative. Neither of them are elemental. Magnetic resonance gives you mineralogical results like chalcopyrite, cobalt. X-ray transmission gives you relative atomic mass or density of elements or minerals. So it doesn't actually give you elements. You use an X-ray transmission response to look at the different densities of different components and make assumptions that the more dense material is ore, and you respond to it that way. In coal, X-ray transmission is used to look at how much ash there is in the coal. So it's not actually measuring the elemental content. Those technologies I just mentioned, like X-ray transmission, XRF, LIBS, near-infrared, a lot of those are used in particle sorting applications. Because they can penetrate through small particles. They do struggle to penetrate through half a metre of rock. The advantage of the PGNAA is it's extremely high energy, but it's an instantaneous process, so there's no residual radiation. It's not affected by particle size. The neutrons and gamma both have high enough energy to penetrate half a metre of rock. So if there was a continuous flow, if someone had sliced a lens-shaped sliver of rock out of the ore body, like drill core, and fed it continuously along a conveyor, it would give you the same reading as if that material was crushed to micron size, okay? Because the system doesn't see particle size, it only sees elements at the atomic level. So what we're talking about here is a technology that's proven to be safe. We have over 300 installations in the cement, coal industry, now 80 in minerals. So it's been used for 25 years by us, and as well as other vendors. So it's well proven. It's proven to be safe. We're not aware of any incidents that have occurred. There's a few potential ones coming up, but it's a different story. We know it's representative because we've rearranged material on a belt and remeasured and got the same results. We've put big rocks, we've crushed it, we've put fine material in, same results. The advantage of the system is that for certain flow rates, you can measure over certain time frames, so you can work out the tonnes that relate to each measurement. Okay, now each measurement is a continuous accumulation of spectral data averaged for that time frame. So over 30 seconds, we're averaging the spectral results. We're taking inputs from a belt weigher, so that if there's variability in tonnes per hour through that time, we take that into account. So 8 tonnes, the one that's circled, is the sorting increment that New Afton and New Gold are using at the moment. What do we measure? So this is a periodic table showing the relative performance of different elements with this technique. So typically we're measuring sodium, potassium rows, and some of the ones below. But sodium is the lightest element we measure on a routine basis. We can actually measure nitrogen and carbon. So they're two elements we're now doing more work on. Nitrogen is one that we very rarely get asked to measure, so we're not even sure how much demand there is for that. It might be in the urea or the fertiliser industry, but there hasn't been too much need for it to date. Anything that's blue or white are elements that don't respond well to the technique. In other words, they don't absorb neutrons, or they don't give off gamma radiation sufficiently reliably to be able to measure those elements. Some elements we are actually measuring, the red ones, so the hotter the colour, the better we can measure those. So we are measuring mercury in iron ore in Austria at the Erzberg operation down to 1 ppm. And that's on a 2-minute measurement increment. Okay, so the colour of the element helps us to determine the relative scale at which we can measure those. We can measure copper, nickel, chromium, down to tens of ppms accurate. So there's various elements indicating various compositional traits of the ore or waste that we can measure. Sometimes it's correlations if we can't measure an element directly, like platinum. You would have seen earlier we've supplied to the platinum and gold industry, sorry, the platinum and lithium industry. We're not measuring platinum or lithium at either of those sites. We're measuring elements that are proxies for those elements. So in lithium, we've sold 2 units in Western Australia. They have a formula where we input all of the elements that we can measure, and they say, based on that formula, I can calculate, because of mineralogical associations, I can calculate the spodumene content, which correlates with the Li2O content. So our measurements of the other elements gives them an accuracy or about 96% correlation with the Li2O grade. So that's good enough for process control. It's not intended to be an absolutely accurate measurement system. The platinum and the palladium, we're calculating from copper and nickel content in some South African platinum material. This is really just to show what sort of variability we're seeing in the feed to different plants and different commodities. So top right is each one of these represents 24 hours of 2-minute data. So the top one is Cepon. Cepon is a controlled feed. Every half an hour they composite the tonnes and grade that they've put into the plant and then modify the feed blend for the next half an hour if needed. If the metal tonnes feeding the plant, being a leach circuit, if the metal tonnes feeding the plant are within their target range, they don't change the feed blend. If it's trending out of the range, they then modify the feed blend to adjust for that. They don't want to overload the leach circuit with copper metal. The lead zinc is an ISO, so that's a day in the life of the heavy medium plant feed conveyor when it was running. And the iron ore one is one of the Pilbara iron ore sites. You can also see that the 2-minute measurement increments relate to different tonnages. So this throughput represents 300 tonnes an hour, this one's 1,000 tonnes an hour, and this one's 3,000 tonnes an hour. So each of those 2-minute measurements represents whatever tonnage goes through in that 2 minutes. People say, well, what's measuring variability important for? We know we're going to get it, we've just got to deal with it. let's just see what happens. We'll twiddle some reagent knobs and hopefully we'll achieve the target recoveries. Well, in practice that doesn't happen. Codelco did a lot of test work because they found that even though their feed grade was 1% each day or each metal accounting period, the recoveries didn't reflect consistent performance of the plant. So when they assessed the variability of the feed grade within those measurement time periods, they came up with this graph which showed that the more variable the head grade was, even though the average was 1% copper, the poorer the copper recovery was during that period of time. So the outcome of this was that they changed their scheduling from the mine to the mill to try and improve the consistency of the ore coming to the mill. Okay, so I mentioned earlier that the technology has many applications, and the diversion or the bulk sort is one of those. So this is most passive to most proactive in terms of top to bottom. So diversion is considered a fairly active response to data. The other ones are basically, is the quality what we expect? Let's measure the input and the output and optimise the process. Okay, we've got material coming in, let's make decisions on the increments. Blending and additive control is like the SEP application. The blend, the quality we're getting isn't what it should be, so let's change the blend. Or additive control, like material going into a smelter. Okay, we need to adjust the additives to correct for the chemistry to make sure we have the appropriate chemistry for the furnace. And feed forward control is we're measuring something and then telling the operations in 20, 30, 40 minutes, this is going to hit you, so you need to make some decisions. One of those could be, okay, the material is particularly high in silica, so it's harder ore, so we need to slow down the feed rate to the mill, otherwise we're going to overload the mill. Another one could be, okay, we're getting a high slug of talc, we might need to increase the talc depressant to the first depression tank for talc. Any number, there could be a high slug of copper coming through, so maybe we need to change the reagent regime to cater for that extra copper metal coming through. So there's a whole range of parameters you can adjust based on knowing what the quality is before it actually hits your system. So bulk diversion is fairly simple. Conveyor, sense or measure the material and then make a decision on where you want that material to go. There isn't just one application for that. I mean, obviously you can do that on a feed conveyor and then stockpile the material into different grades. You can remove waste, high deleterious components. You can put it on a pebble recycle circuit and say, if that pebble isn't worth putting back in the mill, why am I occupying mill capacity with that pebble when I should be rejecting it and replacing it with ore that actually has metal in it? Product quality bypass. This is more where iron ore, bauxite applications where material comes from the mine and some of the time it's already product quality. So why beneficiate it when you don't need to? So we have an application in South Africa where we're saving $7 million a year by not beneficiating 5 million tonnes of product quality iron ore. And sending material off to different processes. So if you have some marginal ore that can be upgraded, well then you can divert that to that process. So the key requirement for an effective bulk diversion process is three things. You need a sensor that's representative, responsive, gives you real-time information. You need a diversion mechanism that is responsive, is able to respond quickly, so that if you have a 30-second measurement increment, you don't have a diversion system that takes 10 seconds to move from one position to another, because that increment won't be accurately selected. So that's becoming the limitation now. We're not seeing too many operations who have got diversion systems that are responsive enough. So they want short measurement times, but they can't benefit fully from those because they're not able to divert quickly enough. So unless your diversion system can respond within less than a second, you're actually introducing another error in selecting that increment. The key thing in any bulk diversion application is the strategy. You don't want to apply a cut-off grade based on other parameters. You need to take into account the variability on that scale and pick an appropriate cut-off that's appropriate for that material at that time in the operation's life. So you would expect to use a different cut-off from day one than you would in the last years of the operation, where they want to process all the material that they can because capital's been paid off and you've only got the operating costs. So the other thing is materials handling. You need to realise that if you're going to divert 30% of the feed to the mill, how are we going to manage those tonnes? We can't just put them on a little stockpile with a little front-end loader if it's 30% of our throughput. We need to put in place conveying systems or other means of getting rid of that material. We've mentioned the other things before. Acceptable tonnage, reject and metal recovery factors. We get mining companies saying to us, we would like to reject 10% of the material but only lose 5% of the metal. And we'll say, well, how do you know you can achieve that? Well, we don't. But those numbers sound about right. So it's okay, well, it's a good ideal, it's a dream, but let's look at reality and say, okay, you may need to measure the material at that scale to understand its variability, to then develop a strategy. And you can do it as an iterative process, because even just measuring in real time, you can still use those other benefits of the real-time data. You can feed forward, you can do reconciliations, metal accounting, and all those things with that data while you're developing a bulk ore sorting strategy. And obviously we don't want the mill to run out of tonnes. Okay, so sometimes we will override a cut-off because the crushed ore stockpile is low and we just want material going to the mill to keep it running. So based on where we were discussing the use of units, as soon as material's on a conveyor after a crusher, that can be underground, it can be on surface, putting in diversion systems at the end of those conveyors, pebble recycle circuit. The green lines basically show the flow of information, so what we do here is feed back to the mine, maybe change the blend of ore if they're not providing the quality the mill wants. How would that be? The mill determining what the mine sends them. There's an innovation. Real-time data being collected and being used to control feed rates, the grinding mills, flotation circuits, that sort of thing. So there's many different ways of using the data. So just for the last 10 minutes or so, we'll talk about the New Afton operation. The advantage New Afton have is that the mine has a greater capacity than the mill. So it's about 25% more. So they have the ability to potentially divert 25% on average of their mined material, and they can still keep the mill running. So the advantage they have is, well, firstly, it's a block cave, so they know they're going to get waste. Okay. There's no doubts. In the block cave, at some point, you're pulling out of multiple draw points, they're going to turn to waste. So it's a great application for the technology. They did look at particle sorting and said basically we can't particle sort 1,000 tonnes an hour effectively and economically. It's just not going to work. So they did some of those studies already and they realised they need to look at bulk analysis and bulk diversion. How did they evaluate it? Okay, well, we think bulk diversion will work, but what data do we have to look at? So they looked at samples they were taking from draw points. They had nearly 2,500 samples collected over a long period of time. Each sample was collected at the end of a shift for a draw point. So during a shift, 300 tonnes would be mucked out of that draw point into an ore pass, and then the sample would go in and take a not very good sample, but a sample nonetheless. So grape sample, whatever you want to call it, but it gave them some data to consider. So they said, okay, if we use the 0.3% cutoff, how much would we have diverted or selected as being unsuitable to process, and how much copper metal would have been in that material? So you can see that they would have diverted 10% of the tonnes, but only lost 1.5% of the copper metal, and the feed grade would have increased in the 90% of the material from 1.1 to 1.2% copper. So they said, great, that's all the justification we need to go ahead with the project. Initially they planned to divert waste, low grade, to particle sorting, which was still to be assessed further, and then the high grade would go direct to the mill. That was based on a 300-tonne decision. What we're giving them is every 8 tonnes. So we're giving them a much higher level of selectivity to base their bulk diversion decisions on. So the first thing, they sent us samples to do test work. To get samples, we need the customer to crush them, sub-sample them, so that we have a lab assay to calibrate to. So we received these 6 blue crosses as calibration samples, and these 3 samples as blind samples where they didn't tell us the grade. So we set up calibration, tested the blind samples, and they were very happy with the performance. Each sample was about 180 kilos to 190. The reason for that is that's the equivalent of 1 metre of conveyed flow at 1,000 tonnes per hour at that belt speed. Okay, because that's what the analyzer will see at any given point in time, so that's the sample size we asked for. The samples are tested in a production analyzer, so that analyzer is the one that would have ended up on site. Interestingly, there's a gold graph there. We were able to calculate gold from the copper and sulphur. Now, they had calculated the gold themselves using their lab data. The lab data was the red lines. Their calculation of gold was the dark blue, and calculation of gold from our analyzer results was the light blue. And I guess the reason we're so close to theirs is because we used their formula to calculate the gold from the copper and sulphur. So that demonstrated a reasonable estimate of the gold grade. And this is the accuracies we achieved from that test work. So basically for that range of copper, we achieved a measurement accuracy of 0.03% copper. That's the correlation between the lab and the analyzer results. For sulphur, accuracy 0.07% sulphur. Chromium, these are in ppms. So they're the ranges of chromium and nickel, and the accuracies for measuring those around 15 ppm. And for gold, the range was between about 0.1 and 1.2 grams a tonne, and the calculated gold result was within 0.15 in terms of the root square deviation of those results. So they were happy to proceed. Picture of the installation of the analyzer underground, material coming out of the gyratory crusher. This is an image representation of their block cave. This green material is supercritical. It's a waste and it's pickrite. So it's a particularly nasty waste material, and if it goes into the process, they lose all copper recovery. So that's why they wanted the nickel and the chromium results, because the pickrite has elevated nickel and chromium, and if they see that coming out of the mine on their conveyor with a sensor on it, they know that it needs to go to the waste irrespective of the copper grade, because they cannot recover the copper from that material. The plan was to divert into 3 destinations: waste, low grade, high grade, and the low grade or intermediate grade, they were looking at a 2-stage particle sorting process. That hasn't happened. They're still trying to work out if they can justify it. So this is how it's going. They're measuring every 30 seconds. The results are correlating well with sampling they're doing off the conveyor. They're fine-tuning the lag time between the analyzer and the diversion system, because the analyzer is 6 minutes travel time back down the decline from the diversion point in this conveyor. Crunched ore stockpiles in the background. This is the material that's being diverted that's considered waste. Their diversion system is a bit different. It's actually a hydraulically actuated series of lifters that lift the conveyor belt up, flatten it, and press it up against a fixed plough. Okay, so you can see the plough here. So that plate doesn't move, but when they want to divert for 30 seconds, the belt is lifted up, flattened out, material is ploughed off for 30 seconds, and then it drops down again. Whether that actually happens within a second, I don't know. So that they're still fine-tuning their system. One of the problems is the conveyor is, from underground, is in 4.2 kilometres in 3 legs, and the analyser is installed on the second last conveyor. Because on the last conveyor, it's the main decline into the mine, and they didn't want to put it in that location because of infrastructural risk, potential for collision with trucks and various other things. So that's why there's a 6-minute lag time. Normally, we would put it at the start of the conveyor, at the end of which you're diverting, because then you have more confidence in your lag time. If you've got to go through it, chutes and other transfer points, you've got more delays, some of which you can't control. Depending on the flow of the material, etc., you might get a couple of seconds of delay longer than you expect, and therefore your selected increment isn't as accurate as you hope. So just summarising, what we're trying to do is supply a technique that's customised for this application. So for bulk ore sorting over 30 seconds, it's a very high specification. It's a different specification to the Sepon one where we're measuring for 2 minutes, because over 2 minutes you can use less detectors, for example, and you're averaging over a longer period of time. So that measurement can be quite accurate. When you come to 30 seconds, you're sacrificing time, and time means the number of counts. So to get more counts over a shorter period of time, you need more detectors or a larger source or some software modifications. So that's why the systems are different for each application. All of these things we've discussed, so the last point there is AI options to assist plant control. So we are working with some companies in the AI area to help us model our clients' processes so we can try and come up with improved responsiveness to real-time results. Key thing here is we're looking at small increments. So 10 tonnes is about the size of a loader bucket, and we're making decisions on every loader bucket equivalent with an accurate measurement. Variability is always higher than expected at operations on that measurement basis, because in their minds, variability is the difference between that block grade and this block grade, and they've all been averaged, so it's not as high as it actually is on a conveyor. And variability is manageable if you measure it. If you're not measuring it, there's nothing you can do about it except respond to it. Again, most of these I've already discussed, so I won't go into it. Okay, are there any questions?